Okay, this is lecture 16 for power. So this way. Okay, this is lecture 16 for power. So previously, in the previous lecture 15, we have studied the introduction of a power consideration. So instantaneous power of certain elements can be considered as just a product between its terminal current and voltage. So that was explained with an analogy with the roller coaster problem. So if everything is quite just ballistic, then our particle will move this way. In this case, actually energy is conserved and no energy dissipation is observed. However, in realistic case, we have friction. When we have friction, actually this amount of potential energy is now converted to other form of energy, and in the case of our typical electronic device such as MOSFET, usually this kind of dissipated energy is converted into a form of heat. So heat is related with temperature, and as a result of this operation, we expect temperature increase when you operate your chip. So simply speaking, you know that when you have a CPU, and when you run certain hard-loaded application, then you feel that okay, the temperature of your CPU is increasing. That is related with this power dissipation. And once we understand the power dissipation at a given time t is given by this one, then now we can think about a specialized case of switching. So the logic gate is switched between 0 and 1, and it is loaded to certain capacitor called C. In this case, if we have certain frequency f and corresponding period capital T, then we can understand the switching power can be obtained by this product. So if you have a higher capacitor, then you will have larger power consumption, and you have quadratic dependence on the operational voltage and linear dependence on the frequency. That was covered in our previous lecture. And at the end of our previous lecture, we have thought about the total power consumption. Yes, if we consider total power consumption of our logic, then it can be divided into two parts. One is so-called dynamic one, and another one is static one. Static power, dynamic power consumption. So static power consumption means that we just apply DC bias condition only and do not introduce any kind of a signal in it. Even in this case, we have power consumption. So this will be discussed in our next lecture, not this lecture 16, but we will consider it in lecture 17. And today we will talk about dynamic power consumption. And dynamic power consumption means that we just change our signal in real application, and in order to operate that system, we need a certain time varying consumption or power consumption. Yes, in this case, dynamic power can be divided into two terms like switching, switching, and another one is short circuit current. However, short circuit current or short circuit power consumption is just showing certain case like this. So you know, an input signal is entered into this inverter, and you know that if this is really 0 or VDD, only one of our two transistors is turned on. However, let's say that intermediately, let's say that we just apply half VDD, then what will happen? In this case, NMOS will be weakly turned on, and also our PMOS will be weakly turned on. In this intermediate state, then we can expect certain current conduction from our VDD node to the ground. So in this case, we will have a although that is quite a short time, because you know, once the input voltage touches half VDD, it will either go to VDD rapidly or go down to the ground rapidly. So that is quite a short time. However, during that short time, there will be current conduction that is represented as short circuit power consumption. But in usual cases, this short circuit condition or short circuit power consumption is quite much negligible. So when we consider dynamic power consumption, then it is more or less similar to the power switching power consumption. Okay, so today we will mostly concentrate on the switching power consumption. Before starting our today's lecture, we wanted to talk about certain real world problem or real world data. So maybe 2 days ago, there was an announcement about Apple's new chip called M3. So however, this is the previous generation, not very much updated, but I will use this one because it has a much beautiful graphs. So Apple M2, actually it is the entire chip, so-called application processor. So it contains the CPU, GPU, and many other components in it. But now we concentrate on its CPU performance. And now we can draw certain graphs like performance versus power graphs. So although that is normalized, so shown here as a relative way, but this axis is really performance. So high performance is our desirable one. And what is this axis? This horizontal axis is power consumption. Of course, the desirable direction is like this. So we wanted to have low power consumption and at the same time high performance. So although here written as performance, what is actually the performance? The performance means that actually the operational frequency. How can we fast perform certain arithmetic operation or logic operation? So it has its former version M1, and it is just an advertisement slide. So M2 says that, okay, given power consumption, our new chip at the time can achieve to about 20% to 18% higher performance at a given power consumption. That was the advertisement. But what I wanted to say is, okay, this is a generation to generation comparison, and if we let's assume that there exists a certain technology or certain chip which has this kind of graphs. So say that yes, then For example, if we have such kind of thing, in order to get the same performance of this new chip, then in order to get the same performance, we must spend more power. On the other hand, in order to get, in order to spend to same power consumption, then our performance will drop out significantly. So this kind of trade-off relation between energy efficiency and power performance is once again confirmed in the real world data. However, the reason why I just bringing this slide is not just repeating their advertisement, but please have a look at this x-axis value. So you can see that its value is like this. For one CPU, the expected power consumption is more or less 10 or 20, 30, 40. So this is the typical number we have to keep in mind. So, and please note that although the M2 has many different components in it, so it has total transistor count is 20 billion, so about 20 billion. And you know, this is around only, this is only the part for energy consumption for the CPU, but anyway it is around like 15 watt is a maximum power consumption. Okay, so now let's go to the textbook content, dynamic power. Okay, dynamic power, that is once again can be decomposed into switching power and short circuit power. However, we will neglect this short circuit part because that is not that much important in its magnitude. So we will just use switching power, and switching power, you know, that was given by something like activity factor and frequency C and our operational voltage square. So that was the simple rule to calculate. So in this textbook example, we have just we have just 1 billion transistor system. Okay, so in this 1 billion transistor system, we have 50 million logic transistors and 950 million memory transistors. Then from these two information, try to calculate dynamic power. That is the example. So it is assumed that since the textbook is somewhat outdated, so technology is 65 nanometer process. So I wanted to ask you once again, what is the technology adopted in this M2 processor? So usually we say some nanometer technology to represent certain technology, device technology. So when you go to here, now we say that 65 is the number for specifying this process technology. And when you come back to this M2 processor, the value is now 5. So compared with our previous number 65 nanometer, so it is shrunken quite significantly. And in the case of our M3, so do you know what the number is? What is this number? So it was just announced yesterday, or some sense the day before yesterday. But anyway, this M3 has used the technology advertised as 3 nanometer technology. So you know that if we have different technologies, then we can get quite much different numbers. So in terms of power consumptions, please have a look at this one once again. So now we have just 1 billion system, and average width in this 65 nanometer, the design rule, the basic unit of design rule lambda is 25 nanometer, and average width of our logic transistor is 12 lambda. So what is 12 lambda? It means that it is corresponding to 0.3 micrometer. Okay. So in the case of memory devices, we have much smaller ones like just 0.1 micrometer devices. And we assume that in order to calculate the power consumption, we must know these four quantities. So frequency, how fast is it? So the operational frequency is 1 gigahertz. So we will just say that 10 to the 9 hertz will be used for this calculation. And what is operation voltage? Let's assume that this is just operated at 1 volt. Okay, now we have squared 1 volt, and now we have two types of devices. One is logic device and one is memory device whose activity factors are different. So in order to calculate this one, then we must calculate its activity factor for logic and the capacitors for all logic transistors, and 1 volt squared and 1 gigahertz, so 10 to the 9 hertz, and plus another one is memory device, and that is given by 0.02 times C of contributed from all memory devices, and the same squared 1 volt and 1 gigahertz. So then how can we estimate this capacitor? Of course, we may have a good way to estimate these capacitors, because we know every device has its own contribution, but in average, let's say that every device has 0.3 micrometer long gate, and for each gate unit gate length, say that 1.8 femtofarad is contributed. Then in this case, for logic device, we will have just this number for per transistor capacitance. So we have 0.54 femtofarad. So no, this is not micro. Femtofarad per transistor. And now we have how many transistors? Now we have 50 million transistors. So 50 million transistors. This femto and this million just combine each other. The femto is corresponding to 10 to the minus 15, and this is corresponding to 10 to the 6. So when combine them, we have just 10 to the minus 9. Okay, so you will get this number out of this calculation. So you can follow the similar calculation, because now we have just 0.1 micrometer for our logic transistor, so we will have just 0.18 femtofarad for each memory transistor. And how many transistors, memory transistor, are there? Yes, we have this number for memory transistors. Once again, when combined this femtofarad and million, then we will have just nanofarad, and just to calculate their product, then you will have this number. So when you just insert this number here and that number here, then it is obvious that about 6 times memory transistors has about 6 times higher overall capacitance. Yes. However, another consideration is logic transistors are more frequently switched on and switched off, so therefore it has higher activity factor than memory transistors like 0.02. So although we have higher higher capacitance, but due to the relatively lower activity factor, their contributions are more or less similar, really comparable, and the answer would be 6.1 watt per this transistor, 1 billion transistors. Okay, so please have a look at it. So where is 1.6? 6.1, and this is just corresponding to this number or this older technology. Compared with this new technology M2 or M3, this is somewhat outdated. However, power consumption is not that much smaller than our current situation. So what is the main driving factor to have much high performance, however comparable power? That is improvement of technology, because they have used older technology and they have used better technology or newer technology. Okay, so that is one thing. Actually, that's the reason why almost 90% of new technology fabrication capability is just transferred to only to the Apple, because Apple has a certain dominating power in the electronics market, especially in this consumer mobile devices. So they have some privilege to select fab, uh, their fab, and since the power consumption and performance is quite important, and the best way to get best compromise between power and performance is having a new technology. That's the reason why they always try to find out to make the contract with the newest technology. Okay. So anyway, technology is quite much a big decision. So as a just the individual designer, you cannot, in many cases, you cannot select the technology. Then from given technology, then you have to do your job to reduce the power consumption. Let's say that you wanted to reduce the switching power significantly. Then what you have to do is, for example, reduce this activity factor, or reduce capacitance, or reduce voltage, supply voltage. Oh, sorry about that here. And another one is we reduce frequency. Of course, reducing frequency is directly related with our performance. So therefore we don't want to compromise it in this way. However, let's think about this one by one. Activity factor estimation. So activity factor once again means that how frequently a circuit is or the logic gate is switched. So alpha, it can have, of course, have a certain range like this. If alpha is 1, then it is given by simply switching power is CVDD squared F. What is it? This is just a circuit, power consumption of a circuit switched by a clock signal. So when we have this condition inverter, and it is every clock it is turned on and turned off switch, then in this case the power consumption is given by this quantity. However, usually we take certain edges to synchronize this system. So let's say that we just keep this rising edge for our transition. Then if a signal runs in this way, only rising and down for clock signal or rising edge. In this case, what we can expect is for real signal, the maximum value maximum frequency or activity factor we can expect for signal root is about 0.5. So alpha equal to 1 is really corresponding to the clock signal. And however, this is once again the worst case we can think. I mean that it is always say that 0 or 1 0 1 0 1 0, but that doesn't happen very frequently. So because when we consider certain information, your information is not like this way 0 1 0 1 0 1 0 1. This one is not a typical way. For example, if you think about processing certain number, let's say that this memory is assigned to a certain number, double precision number, for example, or integer, and let's say that this is yes, and in many cases, your highest bits maybe frequently 0, and you change your numbers in lower bit. For example, let's say that you are learning certain loop like your integer value start from 1 to 10. If you have this kind of operation, you just increase your integer number called II from 1 to 10, then what will happen to its memory device? Then, starting from 1, it will be changed to what? If you increase it, then it will become 1 0. Yes, you have a change, and you have a change here. And when you further increase it, then you will have 1 1, and you will have 1 0 0 and 1 0 1. So are you all with me? Although we are changing our integer variable, however, in terms of our memory system, then we are now changing only small bit assigned to its lower scale, so which has a higher magnitude doesn't change frequently. Of course, this is one case. If we instead of this one, if we introduce a higher increment, then of course that can be changed, and this one is just kept as before. The point is, our signal is not like this way. 0 1 0 1 0 1 0 1. That is not quite much natural. Actually, the natural signal has certain long period of zeros, and sometimes it can have some long period of 1. So what we can expect is, although alpha can be 0.5 for this most frequently changing signal, but maybe alpha can be lower than that. So now we wanted to talk about how can we estimate this activity factor. So now let's say that a piece of I as a probability that certain node is 1. okay, and p bar is the probability to have the value of 0. So that is just 1 minus p. So it's quite easy. I mean that p1 p equal to 0.3. Then what is p bar? Obviously that will be 0.7. So there is no confusion. And now let's say that for one case we wanted to expect certain change or certain change. In this case, in this case we will have a certain switching, but let's say that instead of that, 1 is just moved to 1, or 0 is just moved to 0. So please understand, I just made crude graphs, but let's say that this is time, and this is a previous time instance, and this is a new time instance, and this is a logical level, logical value. So this is a 1 to 1 transition, and this is 0 to 1 transition, 1 to 0 transition, and 1 to 1 transition. So which one is considered as switching, and which one is just stay at the previous case? You know that this is staying at the previous case, and this one is this is 0 to 0. So this is regarded as staying at the previous case. So what we have to calculate is, okay, the probability for certain value 0 or 0 so we have to consider the probability from 0 to 1 or 1 to 0, and this is corresponding to p bar, and this is corresponding to p, and this is corresponding to p, and this is corresponding to p bar. Of course there is no guarantee that this p and p are the same at the different time instances, but we just make a crude assumption that, okay, since we are now talking about, for example, 50 million transistors, or 1 billion transistors, or even 20 billion transistors, so individual motion or individual transition of our transistor is not that much important. Instead of that, just to consider its average value. So that's the reason why we consider probability, and transition occurs from this quantity. Let's say that the extreme case, probability p equal to 0. What is it? P equal to 0 is that in every chip inside our every transistor inside our chip is just having the value of 0. So logical value is always 0. Then what will happen? In this case, there will be no transition, so its activity factor should be 0. And now consider the opposite case, P equal to 1. Then we stated that every transistor is just having output of 1 and no transition, of course. So we have once again 0 probability. So simply speaking, when we have a certain meaningful number of 0 valued 1 and meaningful number of 1 valued 1, then we can expect a transition. Okay, so here we have a bunch of 0 valued 1, and here we have a bunch of 1 valued 1. When we have this kind of system, then we can have certain transition. However, let's say that we have this kind of behavior, then there will be almost no switching. So I wanted to emphasize once again, this is also obtained from an assumption is like this. So previous and uh, previous time instances and present time instances are not correlated at all. So whether it was 0 or whether it was 1 do not make any impact on the present value of our output node. So that is quite crude assumption, but anyway, it is just used in this case because actual calculation of activity factor should be done in a more rigorous way, but right now we just wanted to discuss about general impact of our activity factor. So please just accept for while, just accept this crude approximation. Then if we understand this approximation, then we can say that this value activity factor can be maximized when we have probability of 0.5. Okay, so now say that when you have 0.5, half of them is 0 and half of them is 1 in our chip, and now we have once again half of them is 0 and half of them is 1. However, there is no guarantee that number 1 transistor is also number 1 transistor in this 0 value. It can be either go to 0 or it can be go to 1. Okay, so that's the reason why we have this number alpha equal to 0.25. Okay, please note that how can you, for example, how can you realize this kind of system? Let's make a comparison between alpha equal to 0.5 and alpha equal to 25. In order to achieve this activity factor of 0.5, we must have 0, 1, 0, 1, 0, 1, 0, 1. That is the only way. But in this case, when we start from 0, then only half case we have 0 and only half case we have 1. And once again here only half case we have 0, only half case we have 1 and 0 and 1. There are so many different realization of this kind of constellation. So now we can see that when we consider just two transition, two period transition, then how much 0 to 1 transition occurs. So we know that here we have 0 to 1 transition here occurs once, so they are all related to this one, and this is related this path we have a 1 0 to 1 transition. So we can expect this kind of a thing once again to 1 0 1 0 1 0 1. So when you consider this kind of thing, you can find that if we are concentrating on 0 to 1 transition, you can see that if we expand this tree more and more, then the probability to change it, to find out 0 to 1 will decrease significantly compared with this alpha equal to 0.5. Okay. So now we now understand if we have complete, that alpha equal to 0.5 is really well ordered way, really well it is. Let regular way, it is changing quite rapidly. However, data is not open, and we have different extreme like 0.25 case when we have completely random case. However, as I told you before in the previous one, so our signals is not completely random. So in many cases, for example, if we consider the highest, if we have one integer, and if we consider the most significant bit, so MSB, most significant bit of our integer variable, then it is very much probable to have just stay here 0 or 1, whatever. It does not change very frequently. So in this case, we can expect that the actual alpha would be even lower than this completely random value. Okay? So once we accept this kind of description, then now we can think about switching probability of our p-value. Once we understand p, then p times 1 minus p will determine our activity factor. Then who decides this p? So let's say that we have a certain signal. However, now we have two AND case. So simply speaking, here input A and input B, and we have output Y, and A and B has a probability of 0.5. Let's say that 0, 1, 0, 1. Both of B and A and B parameters or input variables can have either 0 or 1 with equal probabilities. Then what will happen? We will have 4 different cases, and what is the case for having the output value y to 1? In order to make y to 1, the only way is A equal to 1 and B equal to 1. All other cases like 0, 0, 0, 1, 1, 0, we will have just 0 values. So we can say that, okay, probability of y having the logical value 1 will be just a quarter. Okay, because they are all having the same probability. But let's say that in this another extreme case, A is just fixed to 1. Then what will happen? Only B have half probability to have 0 and half probability to 1. Then in this truth table, actually this part doesn't contribute any longer, and we have 2 equally probable cases. A is always 1, only B determines the value of y. So in this case, we must say that P of y variable is just half. So simply speaking, when you consider this 2 input AND gate, not NAND gate, then we can say that the probability is given by just P sub A and P sub B. So are you all with me? Because only when A is 1 and only when A is B is 1, then we have value of 1, output value of 1 of y. So that's the reason why we have PA times PAB. You can follow actually this probability just to follow the arithmetic analysis of our AND gate. AND gate can be considered as a product between three input variables. So A, B, C. Yes, so you can now easily understand. And finally, let's consider OR gate only. So OR gate, how does it look like? A, B, Y. This is 0, 0. In this case, 0. However, we have more choices. 1, 1, 0, 1, and 1, 1, 1. So we have a probability to have 1. So when either of A or B is 1, then this expression shown here just says that this is the probability to have number 0 for our output node Y. So 1 minus that probability to having number 0 is corresponding to the probability having 1 as its output value. So you can easily understand this kind of calculation. So it's not that much difficult. So now let's consider once again a textbook example here. Let's consider a 4 input AND. Of course, AND is not that easy directly implemented with one single gate. So in order to implement this 4 input AND gate, we must have this kind of thing. Like this is NAND and this is NAND, 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 and you know that this is actually NOR. So NOR, usual way we draw NOR is, okay, here we have 2 input and bubble, OR and bubble. However, following the De Morgan's theorem, then that is equal to just bubble, bubble, after that AND. That is equivalent. They are equivalent, so you understand this one. The equation shown here, just to repeat the De Morgan's theorem once again. This is nothing but the implementation shown here. First we take NAND, and NAND after that took the NOR. Then from the De Morgan's theorem, then we can change it to this way, and double application of these bubbles can be cancelled out. Then we will have ABCD. So now you understand this is a correct implementation of your 4 input AND. Then now let's try to have each variable A, B, C, D has a probability to have a point, the output value 1. So P equal to half, half, and half, and half. So since this is a NAND gate, so in the case of a NAND gate, so AND gate has the probability activity, the probability to having 1 as 1/4 or quarter. However, this is NAND, so we must have this 3/4. So now we have this one, and from this one, please consider the activity factor here. Then it's quite easy, because 3/4 times 1 minus 3/4 is a quarter. So we have 3/16 here. Yes, that is not that difficult. So also we can think about this one, this P. Here we have this NOR gate, and first having this P bar equal to a quarter, and P bar is a quarter and takes the AND gate, then we understand the probability is just 1/16. And you know, when you calculate 16 times 15 times 16, that will give us alpha equal to this number. So So now you can understand this kind of thing. So of course, yes, this is a quite a simple example. Let's say that we are now using the real or considering more realistic problem, then this hand calculation is not that efficient to design. So what you have to do is just to learn extensive use of computer programs. So you have a good computer program to estimate power consumption from the given layout. So you have to do it many times to optimize that. But general point is shown here. Uh, Up to now, we have considered alpha, and in the remaining time, we will consider other factors considered in this case c times b square and f. Of course, when you change your circuit design, then you can easily change your alpha value. So this course is basically for designers, circuit designers. So as a designer, you can change this alpha. And another one is here we have C values, capacitors. So if you reduce the capacitance, that would be great to reduce your power consumption. But you know that up to now, just before starting our discussion about power, how did you determine this C value? So your previous criterion to determine the C value was delay. And what is this delay? Delay is directly related with your performance. Okay, so C here shown here is directly related to your performance. However, if you reduce the capacitance or to reduce the power, then there is certain restriction your optimization knob for reducing the delay. Okay, I mean that if your concern is only delay reduction, then you can set any kind of C values just to minimize the delay. But it is not guaranteed that when you optimize your system, your circuit to reduce delay, it is not guaranteed that your power consumption is optimal. I mean that in many cases, in order to reduce the delay, you must spend a lot of power. So what we can say is we must now find some balanced approach between delay and power consumption. Okay, so are you all with me? So this is the one. For example, if you introduce fewer stages of logics or smaller device sizes, then certainly that reduce your capacitance. Yes, for example, let's assume that you don't have any kind of for example, inverter. Then what will happen? If you don't have any kind of inverter, any kind of transistor, then there will be no power consumption. So that is quite easy. So in order to reduce the power consumption, it is desirable to have a fewer number of transistors. I'm now showing our previous lecture 14 slide. Okay, so maybe you remember this one. So when you have a look at it, so it was thought in this way. Here we have the same data path load, And in order to minimize the delay, then we can introduce one stage of inverter, 2, 3, 4, different number of stages. So we find that if we have this kind of ratio between our inverters, then we can minimize the delay. So that was the consideration. However, now our question is, how about the power consumption? Which one will spend more power? Obviously, this one will spend more power, and this one will spend lower power, small amount of power. Okay, so simply speaking, let's think about this one. Okay, in order to achieve the fastest operation, we have to spend additional power. But now let's say that for certain cases, we are really power hungry. Then what we can do now is, instead of taking this the fastest one, we can try to use this sub-optimum one. This is not very optimum in terms of delay. However, it has clear advantages in terms of power consumption. So therefore, although delay is important, but delay is not the only important quantity. We have other quantities to be considered in the realistic cases. Okay. So, simply speaking, since the way to reduce the switching power is using fewer stages of logic and smaller gate sizes, if you have a non-critical path for your performance, then you can sacrifice the speed a little bit and you can greatly improve the power efficiency. That is gate capacitance. Here gate means that your transistor. And wire capacitance is another one. So if we consider, in many cases, we are talking about, for example, here we have one inverter and another inverter like this. We are now talking about how can we minimize the power consumption shown in this highly localized path. Should we introduce a third layer or not to minimize the power consumption by this part? However, in terms of this, or from the viewpoint of entire chip, this is quite much localized. The point is, here we have a certain functionality, and here we have another functionality performed in our chip. Then we must provide a certain load from one part to the another part. So for that purpose, we must run a long wire line, metallic wire. Its length scale will be just millimeter scale. So although that capacitance itself per unit length capacitance is not that high, but since its length scale is much larger, because this is a long line, you know that even this one can be visible. I mean that this is the really certain visible size, and you know transistors in this case, they cannot be seen by our naked eye. So simply speaking, this one contributes quite a lot. So if we have long load, then that is not that much desirable. So better way is to place So frequently communicating signals in a nearby, then we can reduce the path while connecting these two different parts. So this kind of thing, not in the transistor level, but placing, for example, some memory block and CPU block, any kind of thing, into one chip. This is the entire chip, and blocks are located in this way. That is typically called as floor planning. So that is also very important to reduce the wire capacitance, and when you reduce the wire capacitance, then it is beneficial to reduce your delay. And maybe you remember that in several months ago, we had a very good paper by Google to automatize this flow planning using the um, AI technique. So I think that is quite a promising application of AI technique to the design. Anyway, now let's go to the other part. So we are now talking about alpha and C V square F, and we have covered these things. And in this last slide, I think we are talking about voltage and frequency. And voltage, here we have voltage, and even worse thing is voltage is quadratically dependent, or quadratically contributed to our power consumption. So therefore, if we change our applied voltage slightly, then it will contribute to our power consumption quite a lot. So historically, this power consumption has been reduced continuously, originally starting from 5 volt. So it has been reduced quite a lot, and nowadays its value is about 0.7 volt. The only reason we do not reduce this further is we cannot. We wanted to reduce this value even further, but as I told you before, it is not that easy to reduce this value even further. So unfortunately, however, let's say that we wanted to still so pencil is stuck, so let's wait for a while. Okay, so now let's say that still we wanted to, or let's say our VDD is given and voltage is still given, but we wanted to reduce certain power consumption. Then how can you do that? There can be many different ways, but in this slide we just introduce use of voltage domains. Use of voltage domains means that for certain part of our system we use VDD, which is relatively low, and we introduce another part where we have relatively higher voltage. Why do we introduce this kind of separation? It is because if we use high VDD value, then our transistors can show high performance. And if we have relatively low VDD value, then it can be operated in low power mode and energy efficiency is increased. So nowadays you understand there is some certain cores in your CPUs, which one has more concentrated on low power and on efficiency, and another one more concentrated on the performance, so performance core. So if we have this kind of two different circuit systems, then yes, inside it is good to have this kind of separation. But the point is now we wanted to send a certain signal processed in this part to the other one, and from this to this. Now think about this case. We have a buffer. Here we have two buffer. However, this is the boundary between low and high voltage. So we have used VDD high and VDD low. Then what will happen? If we have 0 and here we have 0 and VDDL, and that drive our intermediate output value to VDDL and 0. Then for this relatively low voltage domain, it's okay. But point is, if we have this second inverter, then this VDD low is not that sufficiently high to drive our value to 1. Okay, so are you with me? This one, because from the viewpoint of VDDL, this is really logical high value. However, from the viewpoint of relatively higher VDD high, then this one is not strong logical value 1. This is quite weak, and depending on the situation, that introduce potential problem for our application. So in order to eliminate the problems related with sending the signal from one to the other, then we have introduced this level converter. So this is a level converter, and here you can see that they are cross-coupled. The output, a drain of this P1 transistor is fed to the gate, and drain of this P2 transistor is fed to our P1 transistor. So now you have first relatively low value, so please consider this one. When you have 0 or logical VDDL, in both cases you can find that your Y value will be just 0 and VDD high. So actually 0 to 0, 0 is just converted to 0, but your low logical value will be converted to VDD high logical value without any problem. Okay, so we use this one. And another way is to reduce the power consumption is actually shutting down certain part of your chip. So if we have a certain chip, if some part is not currently being used, then actually we can just turn off the clock itself. If the clock is gone, then what will happen? So clock is the heartbeat of our digital system. If we don't provide any clock to this a certain part which is idle, then that will not process any kind of switching mechanism. So the power consumption due to the switching power consumption will be greatly reduced, actually approaching to the zero. So that is another way we can use in this slide to reduce the voltage consumption. Okay, so finally I wanted to say that frequency. In the case of frequency, it is difficult to reduce frequency. When you say that, oh, I will use the frequency lower than that, for example, 10% reduce frequency, lower frequency, it means that you are just saying that I'm done and I failed to the competition against my competitor. So therefore, it is not that easy to reduce the operation frequency. However, another way, since dynamic power is directly proportional to the frequency, please do not overclock your chip. A chip should not run faster than necessary. Necessary means that, there are some gaming geeks, they are really wanted to learn their game, the highest condition, so best condition they can achieve. In this case, they are willing to learn their chip in the fastest condition. But in that case, they are just saying that I can provide a sufficient amount of cooling capability to my CPU chip. So instead of just air cooling, they can provide water cooling or any kind of some strange ways to cool down their chips. So simply speaking, as a chip designer, so you have to have a certain reasonable value for your operation frequency. So do not overclock, and you must just to meet the operational frequency, not overclock it. And another one is the most important thing from our viewpoint is actually the performance seen by our customers. Okay, not internal performance, but performance felt and seen by our customers. I mean that although we have a certain frequency, operational frequency, but that operational frequency is the one of the most critical path. So if we have, for example, CPU and IO, then although CPU is operated at its maximum frequency, there is no need to operate this IO system operated with the same frequency with CPU. So therefore, we can introduce some appropriate operational conditions for each part, and the overall performance seen by our customer seems to be the same. So that is the trick to reduce power consumption significantly. Okay, so that is a short discussion about our dynamic power consumption. As I told you before, dynamic power consumption can be divided into two parts. However, since the short circuit part is not that much important, so today we have more or less concentrated on switching power consumption. And in the next lecture, lecture 17, now we will move to our static power consumption. And as you can expect, static power consumption is all related with leakage current, and leakage current is not that much controllable by design. So leakage current is more or less a technology dependent one, but anyway, we will study how can we consider this static power consumption. Okay, so thank you for your attention, and if you have any questions, then please feel free to give me a question even after the session is over. Okay. Okay, that's it.